this is how it goes. Let's say that tomorrow you decide to write your own web browser from scratch. The obvious superior choice is to write it in JavaScript and bundle it in Electron, of course. There's also something poetic in having both the trusted and the untrusted part of the interface be in HTML. I'm sure nothing bad could ever come out of that. Now, you might think that when you load a website inside your browser, there's two virtual machines involved. One is running the website's JavaScript, and one is running the Electron application. But on Linux, there's another secret virtual machine hidden somewhere. And the truth is that everything runs on virtual machines and on a virtual machine. And if you wonder what that virtual machine is running on, well, the answer is that it's virtual machines all the way down. Maybe I'm exaggerating, but there really is a curious type of bytecode that you can run in the Linux kernel. Matt Knight is a C programmer that works for a Linux security company and is going to tell us more about it. The title is BPF with Zig, and Matt, the stream is yours.
Hey everybody, so yeah, a little bit about me. My name's Matt Knight, and as Larry said, I'm a C dev working at a Linux security company. I do mostly systems programming. If you've got questions after this talk that you want to talk about with me, feel free to contact me at any of these social media platforms. Usually up for a username close to my name. But for Twitter, I settled on Embedded Boy. So yeah, today. So I've been, BPF is something that's been on my queue of things I've been wanting to learn for the last couple of years. And the company I work for released a free product that uses BPF. And so I thought, hey, you know what? Let's jump right in. I'm by no means an expert on this, but I thought it'd be a good time to do a talk because I've been doing a lot of learning. And number one, I've learned that writing BPF and Zig is a lot of fun. And two, there's not a lot of documentation and resources, and I wanted to make it easier for some people to understand some of the lower level aspects of it. So first, I'm going to tell you what the hell BPF is, and then we're going to go over a couple examples of kind of like they both do the exact same thing, but they use slightly different methods on how to load BPF code into the kernel. And then we're going to kind of talk about where I want to see the Zig BPF library go, and some things that are coming down the pipeline for just BPF in general. So BPF is a Linux kernel subsystem. The name stands for Berkeley Packet Filter, but now it's a misnomer because it's been extended way beyond just simple packet capture. And I think the best description of it is that it's a method to run user space code inside the kernel and to do so safely. And it does this by having a VM or a virtual machine in the kernel. And the way it works is that you request the system to run a certain chunk of BPF code when an event fires in the kernel. And in that process or the request, it goes through a static analyzer called the BPF verifier, which is able to determine if the code is safe or not. And we'll get into that a little bit in a couple minutes. So obviously, from the name, the uses for today have to do with packet processing and networking, but a lot of support has been put into tracing the Linux kernel itself. There are other systems it deals with. It's more than just these two things. There's also integration with C groups. I don't know. I still have a lot of learning to do on C groups, but from my knowledge, it's what makes containers possible. And so you can do like tracing and know which container you're tracing and stuff like that. The reason why you'd want to use BPF is one, you want to go fast. And it's also able to give you a level of observability and at a fine-grained detail that you just can't get from user space. I think we're not going to deal with XDP today, but this is a really cool example. XDP is a subsystem as well in Linux, but it uses BPF. and it stands for Express Data Path, and you can do software-defined networking in it. So you can make routers, you can make your own firewalls or proxies, and stuff like that. And it's really cool because some the like hooks into the system allow you to intercept packets right as they're coming out of the network card. And so that's like from a firewall perspective, you can drop packets before it goes through the Linux kernel's network stack, and before it even goes through allocation for socket buffers. Another really cool like edge case for it too is that if you have a network card that has the drivers support the interface. What you can actually do is you can offload BPF code and data structures to that hardware and execute over there, and just not have to deal with any of it on your own processor. So getting back to some of the safety parts, so the verifier is able to guarantee safety first by putting your code under some pretty restrictive constraints. So the first one being there's maximum 4096 instructions per like BPF program, and another like noticeable one is that before version 5.3 of the kernel, you couldn't have any loops, which is pretty big. And then now after 5.3, they have bounded loops, which are compile time known size of the loop or how many iterations you're going to do. And it's with these sort of restrictions that I think Zig is going to be really powerful at, because the code size is small, and then stuff like inline for loops make it really nice to have the high level feeling of loops without actually creating code that does loops. With the size, I know the size is really tiny, but there are ways around it. So there is something called tail calls, and so the idea is that you can have a BPF program call another BPF program through through like a reference, which is just a file descriptor. It has to be loaded into this program map, and then you can access other programs based off of an index, and max 32, so there is still a limit. It works really well in applications where, like, let's say you're doing packet filtering and you need to catch or determine, you have different things to do. If it's TCP, UDP, ICMP, well, you can have a single BPF program determine which type, and then depending on the type, call another program that does whatever actions you want. The way this works, though, is that there is no return. Once you make a tail call, it completes the other program, and that's it. Next, you might be wondering, like, okay, we got these programs. How am I gonna like deal with it in user space? And so there's kind of like three ways to get information out of a BPF program. The first are BPF maps. They're key value data structures that are managed by the kernel and are read and writable by both the BPF programs and user space. So that's a really flexible mode of communication. The next are perf events. We're not going to talk too much about them because I'm still in the learning process. But from my knowledge is they seem to be one direction, so kernel to user space. And I know that they're implemented by a memory map and then a ring buffer, and so they're very, very fast. The next is a BPF helper call, which I'll talk about in a little bit. And so trace print K, it's really just a debug tool, but it is somehow getting information from BPF programs to user space. And from my knowledge, it's like a syslog sort of output at this path that you see before you. Okay, so I think that's enough of an information dump. Let's get into some coding. So as I mentioned, both of the programs do pretty much the exact same thing. And we're going to be counting different packet types. Woo. So here we are. We have user space and kernel space, and we have our process. So another thing I didn't mention is that all your interactions from user space with the BPF subsystem is done through one syscall. And there's a lot of functionality packed into that. There's so many different functions and that are multiplex through this syscall. So this one, for example, will create a map. Obviously, this is a summary of what it's doing. There's other arguments to go into this. So when we create a map, we get a file descriptor and we have a map in kernel space. Next, what we're going to do is we have our program. For clarification's sake, the program isn't actually outside the process memory. It's just for drawing. It makes a little bit more sense this way. And so before we actually load the program, though, the program, assumably needs to access this map. And so the only reference we have to this map is through this file descriptor. So anytime we want to access it, we actually use the file descriptor and place the runtime value of that in our program. And then we call BPF program load, and then it goes through the verifier, as I mentioned before, and then we have it placed in or loaded into the kernel, and we have a file descriptor to that as well. Next, we need to trigger the program because it's event based, and so we're going to use a raw socket. Raw sockets aren't the same as they're not really the same in terms of like a TCP or UDP because that's layer 4. These are, I think, layer 3 technically, and they get attached to a network interface. For us today, we are attaching to localhost. And then, everyone's pretty familiar with sockets. You get a file descriptor to that as well. And we're still missing that. We still have to attach the program to the socket. And so we can do that through setting a socket option, just attach BPF. And if that's successful, there we go. We have this lovely little picture. So let's go check out some code. So here's our program. We've got some imports here. Important things to note. So first we create a map. We make it of type array, which allows us kind of an index type of interface. And so the other things for creating a map that we care about are the size of the key and the size of the value. And then this is the number of elements that map is going to have. And so here we're going to use an I32 to index and use size as a count value. And then after cleanup, you just close the FD. And here's our program here. So what I've done is I've added a bunch of factory functions to create different instructions, and instructions are just 64 bits. And I'm not going to go line by line here. But what I'm going to note is first we're grabbing a byte which aligns with what type the protocol is. And then we're going to reference our map, and we're going to look up the value. I'll talk about this line here actually in a second. And then we're going to have a pointer to that value, and we're going to do an atomic add of just 1, just to count the packet. And then we're going to exit. So right here, you can see call, and then we have an enumeration literal. So this is called a BPF helper. Now, BPF helpers have a horrible name because you automatically think like a utility helper function. But in fact, they're an enumerated syscall-like function that makes up an interface between the BPF program and the kernel. And so when you are reading the raw instructions, it's literally, this will be like call 5. That's all it does. And these are all predefined. These are the only thing that's well documented in BPF as well, which is nice to have. And so another thing I've left out until here, because it's kind of a small detail, is that when our program first starts, the register R0 is loaded with the address of the context struct. And the type of that struct, for us in our case, because we're attaching it to a socket, is a sock buffer. And that's why we're able to grab this byte. And here, the reason why that context is that type is that right when we load the program, we load it as a socket filter. And so the type of that context depends on the type of program we load it as. And this is one of also the lesser documented sides of BPF. There's a ton of cool sounding program types and map types, but their actual like the details about them, I think you just have to go through kernel source code right now. That's something I want to fix. Here we create our raw socket. I've just made a function for this. We don't have to worry about the details. We attach as we saw, and then here we're just forking ping, and it's going to ping localhost for a little bit for us. And then here we got a really ugly loop that's going through. It's reading from the map at different values that correspond to TCP, UDP, and ICMP, and then just printing them out for us. So if we want to run our program, we can do, also we need sudo for this right now because I don't have the capability set up. So we do sudo zig build run ASM, put in my password. And then here we're printing out, and here we go. We're getting ICMP packets as we would expect if ping is running. And then ping sent over however many packets I set it to. And here we're no longer grabbing any packets. So that's that. That's the main idea behind like just manually doing everything. Now, not everyone, like while the bytecode is portable, not everyone wants to write bytecode. And here we go. And so there have been a couple tools for this. So for the last like 4 years, most people get started on BCC, which is it stands for BPF compiler collection. And it's a Python-based framework, and the way it's kind of similar to everything we've done here. But what you do is you do all your user space stuff with Python, and then you can write your like C for your BPF programs, and you use like Python as like the preprocessor, and then it loads it for you, and it's kind of odd. It's kind of jarring for me because I'm used to low level stuff, and having to deal with like high level abstractions but low level like mindset it's kind of jarring. And so the next thing that's coming right now is something called libbpf. Libbpf is in the kernel source tree. It's a C library, and and so it's everything C, and it does a whole lot for you. The thing though, what libbpf does is that it kind of defines an elf layout where you can lay out different variables in different sections, and then the libbpf will know how to load those values in, as well as there's kind of a defined kind of path style for section names for different programs. So that libbpf can attach your program to a specific, like one of the things you can do is like a trace point. So you can specify that this program attaches to a trace point that lines up with the start whenever you would begin calling the open syscall. So I'm working on getting this sort of functionality down, but I think it's time. Let's look at our program. That's the pure Zig implementation. So we go here, and then it's compiled main. This is how. Actually, I want to show you the actual BPF program first. Probe.zig, and here we go. So couple things to note. Here this isn't super important. Here I'm creating a counters map, and this is kept in the link section, or the section of maps. And then here, this type that I'm saving here is right here. So we got the type of the map type, key size, value size, max entries, and flags, which I haven't actually piped in yet. So that's saved there. It's saved in the map section, and then when the loader reads the elf, it knows to look for maps inside the map section, and can grab all the information it needs about them. Here, in order to do that weird single byte read from the socket buffer, I needed to use an LLVM intrinsic And it works quite well. It looks, you can notice that it looks quite similar to our bytecode here. And the difference here is I'm actually skipping any outgoing packets, and so we're actually going to have a count that is half that of the last program. And then here you can see I've added some nice methods for looking up the index of whatever the protocol is, and then getting that value. And then it's actually really nice. We can just use built-in atomics to do atomic operations, and it works really nicely. Another thing that's important is, I haven't mentioned GPL. If you don't license your BPF programs as GPL, there are a few BPF helpers that you don't have access to, but it's very trial and error. If it doesn't, if you're using things that non-GPL programs aren't meant to use, then the kernel will let you know. And that's that. And then so let's take a look at what it looks like in our user space program. So we've got, so this is actually something where I think Zig just does a really good job. So we got an embed file. So with a lot of the examples I've seen, they'll have the elf object file, and then they'll have their normal program, and then the program will at runtime load the elf file, do all the parsing, and then it does whatever it's meant to do. However, I don't like that. Feels like a tutorial way of doing things. I really like the ability to save a file into the actual elf of the user space program, and then we can even do things with comp time, which is making sure that this is the right file and it has the sections we expect of it. I think I forgot to mention that I have socket 1 as the program section, but that's not super important because we don't have automatic attaching. So here, pretty general start to the program. We initialize our object, and then what init will do is that it'll just create all the maps for us, and then we'll have load, and load will do the relocations of the map FD to whatever programs are referencing it in that program code, and then load the code into the kernel. So this would essentially look the same for every program, which is nice. And then here, same thing, raw socket. We can use a find method here to get our program, and then attach the program to the socket manually. And then here we can grab our map FD as well. And then this is all the same. And then if we want to do just show this off, we can do sudo zig build, I think run compiled. And then here we got packets, and you'll notice it's at half the rate because we're not even caring about half the packets anymore. So that's kind of that. Like, I wanted to kind of help convey some of like what those tools are doing today. It wasn't super obvious. libbpf is like 10,000 lines of C code. And most of it's just elf parsing. It's a lot of noise to get exactly what's going on, and they don't really have like a public standard of what's going on. So let's see. Yeah. So for this library, obviously I want to finish adding all the interfaces for the kernel into standard, or it's the standard library. At type struct was released or like added to master like 2 weeks ago. So it's something that I think would even make it better. We wouldn't have to have those find functions for the object. We could just load the object or initialize the object, load it, and then be able to just reference the maps by name. It would just be really clean. And another thing I want to do is make it compatible with libbpf, because if we do that, other people will have the ability to write their BPF programs in Zig, which is way cleaner and way nicer than just C. And I think I don't know, people might have concerns over like how stable Zig is, or even like the minor security stuff that it does under the hood, or the actual code that's created. But with BPF, it's already a safe environment, so that they can safely make those programs. Another thing I didn't mention, this is kind of the way of how things go. So the issue with all of this is that if we're doing socket-oriented stuff, we're fine. We don't have to care too much about kernel versioning. However, similar to like, we know that within the user space or the syscalls on Linux, we've got Linus protecting us, so no one's going to make any backwards incompatible changes. However, when it comes to like the actual internals of the kernel, we have no such promises. And so if you're running these programs and you're compiling them and they're expecting a certain field of a struct to be at a certain offset, then any kernel dev they could add in conditional compilation for that struct. They can add field. They can remove the field that you're referring to. And so we're like, from one kernel version to the next, we could be like the ABI doesn't line up anymore. So this thing called BTF has been created. Stands for BPF type format, and it's pretty much just a debug info for all the types that you're using. You'll have like using the task struct in the kernel, and then you'll be accessing this field named this value at this offset. And then what the idea is that you'll be able to have all the type information from the kernel that you're currently running on, and you'll be able to match up, and the field may not be available anymore, or it may have moved. And if it's moved, the offsets can be fixed for that. So you can have, I think the term is compile once, run everywhere. This is kind of like getting this to work will really make, and then this to work and embedding the BPF program ELF object will make Zig and BPF just meld together perfectly. The only thing, like, I still have some figuring out to do here. The downside, the only things is like in libbpf, there's a bunch of BTF handling functions, and I know that there's a bunch of BTF functions within that BPF syscall, so I don't know whose responsibility is what in that regard. The other thing is, like, BPF is moving fast. I think there's more and more talks about it at Linux conferences all the time. Some of the things is BPF Linux security module integration, I think, was added as of July. Sleep, like the ability for BPF programs to sleep, which is a huge feature. I think that it's either the PR was like just last week, or it was added to the mainline kernel last week. And the other thing is the verifier does continue to get smarter. We were able to that relaxation from no loops to bounded loops was because people were putting in tons more effort into making it smarter. And so in the future, what you'll have is you'll be able to have larger programs and not have to care about the nitty-gritty details as much. So I think, yeah, that's me. And if you have any questions, please go ahead.
Thank you very much, Matt. Okay, so let's move to the Q&A. Just remember, if you want to ask a question to Matt, please remember to tag me in the chat message. And don't forget, I'm not only looking at Twitch, but also Discord and the Zig IRC channel on Freenode. Okay. While we give a little bit of time for questions to build up, Matt, I have the first question, I think. Interesting that the kernel verifies the license and wants the 3 magic letters there. Yeah. What do you lose access to if you are not using? Like, actually, wait. Let me rephrase the question. First of all, does it have to be GPL? Like, if I put MIT there, am I going to get any restriction? And after that, what restrictions am I going to get if I get any?
Yeah, I think the restrictions mostly have to do with I think XDP. I don't have a list of everything there.
Sure.
I generally, the way I approach it, I mean, if you're writing bytecode, you're dealing with the kernel. So by definition, it's a derived work. So I don't actually know how people are able to that's an option given to you, and depending on the license, you are exempt from certain things. So I don't know from the kernel dev's perspective, like how you could create a non-GPL BPF program. But yeah, from my knowledge, like it might not be too much that you lose, actually, from what I've read, but that's still more research into that.
Okay, that's interesting. I mean, so there's a system. I find it funny also that you have to, since tracks can change layout, then you need to find a way of getting back a name mapping for the offsets, which it's kind of hilarious because it's just use JSON. I'm joking, don't. But
just a comment though, just to say, like, just because the actual BPF program might have whatever you write might have to be GPL, your user space program can be whatever you want.
Okay.
Just wanted to clarify that.
I see. Though very curious that now you have to check the magic letters. Okay, so let's see which questions we have now. Is there something special in your build.zig file?
It's surprisingly simple. I'll show you guys right now.
And also, this is a good excuse for me to show the new transition for the Q&A.
Oh, nice.
Let's go
perfect. So like all I'm really doing is there's BPF, little endian and big endian, and that's about it. And freestanding. Oh, also you only release fast because there's no way you can have like any of the release safe code in there, just because it's freestanding. But this is about it. If I think there's a couple things I need to add to the standard library. I think there's a couple like function calls that aren't in there yet that I'm using right now. But yeah, like it was surprisingly easy. Like I was like, I don't know if I'm going to get the right output or the sections are going to be right, but the Zig compiler outputs the right code. It outputs the BTF information, all the relative stuff as well. I hadn't props to the compiler devs, because like I had no issues in that regard.
So that's a noob question, but do I get this right? So we do have a BPF backend then.
Yeah, it's from LLVM.
Oh, right, we're inheriting it from LLVM.
Yeah, for a while, it was kind of odd where for the Linux kernel, you'd use GCC for compiling it, but then for all the BPF stuff, because GCC didn't have BPF until I think recently, so everyone's had to use LLVM for dealing with that. And there's a couple hacky things that you need to do to like have that work nicely with the includes. Darnimator was telling me about it, but I don't remember all the details.
Okay, let's move to the next question.
Sure.
Let me see. Okay, this one is from Andrew. Can you give an overview of the capabilities of BPF? What kinds of crazy things can we do with this?
So the number of helper function calls, I think there's about 130. This can be, I think some of the bigger ones I remember is you can get access to the task struct that's related to the PID that your event is related to. All the XDP stuff is very cool. Then there's all the tracing. You can get for the tracing, you can use K probes, U probes, which are I'm again not I understand the basics, but I haven't done extensive work with them. But they're like dynamic probes that you could do. You could do a bunch of you could get the full stack or the stack trace from the kernel for different trace or points within a user space program. You can hook to the enter and exit for different syscalls, and I think that's all I know of right now that I can think of. And then then there's just like a ton of networking. Oh, and there's like one weird case that was added a while ago, and you could interface with the IR Blaster Linux subsystem, like for the little IR like controllers. I don't know what that's all about, but it's in there.
I think there's also another interesting use case that I stumbled upon recently, which is not strictly kernel related, but it is related to the BPF bytecode. When I was investigating, just so that I don't look like a complete ass while Matt talks about it. And apparently there are at least one blockchain that is using the BPF bytecode as their language for implementing smart contracts, or whatever they call the scripting capabilities that some blockchains have, which is interesting. They are using BPF because they kind of have some of the same constraints that you kind of have in the kernel. You don't want it can't crash, it shouldn't crash. You want to limit the amount of computation that the script uses, etc., etc. So that's also, I think, another interesting use case.
Yeah, I think I'll also like take from watching the talks. I think I meant to plug in some of the talkers that present on this topic a lot, but from like the people working on BPF, they're kind of seeing this as like the next move for the Linux kernel, like having BPF programs kind of replace the kernel module overall. I think actually maybe not quite, but creating like another way of safely doing that. And so I think they even, like, I've heard mention of, they want to be able to do like device drivers in BPF, and just have it like have it be able to interface like the entire kernel. Yeah, like I mentioned, like the BPF security module is just added, so that's like a huge new swath of abilities that BPF can do, and wanted to make that note.
Mm-hmm. Okay, we have another question. Matt, would it be possible to implement a custom protocol besides the IP layer with BPF?
I think that's totally possible, especially like if you wanted to make alterations to like TCP, you could totally do that. Actually, now I remember some of the BPF helpers, you can change the actual body or the data in the message, and then you can a nice little BPF helper to help you recalculate the checksum. So you can do some really funky stuff in that regard, and you can like in terms of the networking, it's very, you can have a lot of like read-write access. The tracing is very read-only, but there's possibility to do stuff like that for sure. That's very very much under like the XDP umbrella.
Okay, awesome. Felix is saying,
yeah,
that makes some project of mine easier. Okay. Okay, then I think that's all for the questions. Thank you very much, Matt. Is there anything else you want to say before we leave?
Thanks for having me on. I really enjoyed myself, and hopefully I'll have more to talk about in the future.
Sure, I would totally be happy to have you come again in the future. Thank you very much.
Thanks.
Bye.
Bye.